Okay, guys. Let's go ahead and just jump in and do a bunch of problems. Like I said, the first couple of videos are going to focus on what I called in the last video the first fundamental theorem of calculus. And that is when you want the area on the interval a to b of the function f of x, we have to anti-differentiate and take the difference, okay? And it's very, very important that you remember that the first fundamental theorem of calculus, that any definite integral right here is an implied difference, okay? By the way, that should make sense out of that property that we talked about in the last section, or in the last video of my 5.1 to 5.2 videos, that if I have a to b f of x dx, and I flip the limits of integration, like I go from a to b and change it from b to a, that makes sense out of why I have to put a negative out in front of there, right? Because if I flip the limits of integration, I have flipped the difference. And what happens when I flip the difference? I get a negative, okay? Like I said, once you introduce the first fundamental theorem of calculus, those properties, some of those properties wind up being much, much easier to understand, okay? So you need to go back and look at those, but they'll come up as we walk through a couple more problems. Let's go ahead and do the interval -3 to 0 of 4x to the 1/3 dx, okay? Now remember that anytime I have a power rule, and here's the hard thing about when you're doing antiderivatives, is it's real hard right at the beginning to remember which way to go, okay? Because remember that when I'm dealing with the derivative of x to the n, it's in x to the n minus 1, okay? But when I'm dealing with the integral of x to the n, it's x to the n plus 1 over n plus 1, and then of course since that's the indefinite one, it's plus c. So here's what I need to do. I need to basically ignore that 4. I either need to pull it out or just bring it along for the ride. I'm going to go ahead and bring it along for the ride. And what happens here, I didn't need to do that, I need to go x to the 4/3 over 4/3, okay, from -3 to 0. So if n was 1/3, n plus 1 is 4/3, right? So this winds up being your x to the n plus 1 over n plus 1. Well, when you divide by 4/3, you're multiplying by 3/4. So that's really 3x to the 4/3, -3 to 0, okay? And then I just need to pop it into the implied difference, right? Top one plugged in, minus the bottom one plugged in, okay? And basically that's what you get, okay? Now remember that the moment that you take that to the 4th power, that's going to become positive inside there. Remember, 4/3 is an even power, so your answer is ultimately going to be negative, okay? And you could, of course, plot that into your calculator and get a decimal approximation. There's really no nice, clean way of actually doing that. So let's go ahead and do that. We know that it's going to be -3 times -3 raised to the 4/3 power, and that winds up being -12.98, 0. Okay? So that winds up being, I mean, the decimal is nasty, but that's really the only thing that's nasty about it. It's actually pretty straightforward. Let's go ahead and do, let's go ahead and jump right into some nasty ones. What do you say? I knew you'd say yes. Let's go ahead and let's look at the integral from 0 to 1 of 1 over x squared plus 1 dx. Well, does anybody happen to recognize that? Well, remember that the derivative of arctan x is 1 over x squared plus 1. So the integral of that has to be arctan, okay? So that winds up being arctan 0 to 1, okay? Or I mean arctan of x. Gotta got to have a angle measurement expression. And so we have arctan of 1 minus arctan of 0. And so we have pi over 4 minus 0, or pi over 4. Okay? And so the area under that curve, and you remember what that curve is, right? Y is equal to 1 over x squared plus 1 is the Witch-of-Agnesi. Okay? And therefore we have, you know, it kind of comes up and does that number right there. So really you were worried about that area right there from 0 to 1. Okay, and then the derivative, I mean the integral of the Witch-of-Agnesi parent function happens to be arctan, so it winds up being really, really straightforward. Okay, well how about something just a little bit more, I mean of the same variety, but let's go ahead and make it just a little more interesting. Okay, do you happen to remember that one? Well, that happens to be, that integrand right there happens to be the derivative of arcsecant. Okay, so we know that arcsecant x from root 2 to 2. Well, that means that I'm looking for arcsecant 2 minus arcsecant root 2. And of course, I never like dealing with arcsecant when I don't have to. If that's arcsecant 2, that's the same thing as arccosine 1/2. And that's the same thing as arccosine root 2 over 2. Well, arccosine of 1/2 is what? Well, it's pi over 3. So pi over 3, and arccosine of root 2 over 2 is pi over 4. Well, that's 4 pi over 12, and that's 3 pi over 12, the difference of which is simply pi over 12. Okay? Now here's the great thing. Your calculator actually does all of this. Okay? So if you actually wanted to go in here, and let's go ahead and just plot this in as a function, and then we'll deal with it on the home screen as y1. So we have x squared minus 1. Okay, so let's go ahead and go to the home screen. And I know that if I go alpha f2, see that function integrate right there? Fn stands for function, integrate. The reason that they put it like that is your calculator didn't always give you a nice, neat integration symbol like this. Previously, it said Fnint, and you had to, like, you know, put in the function, comma, the first limit of integration, comma, the second limit of integration, comma, and then the variable that you wanted to integrate with respect to. It's much, much nicer now. It actually looks like an integral, and so we just go ahead and plug it in there. We go root 2 to 2, because those were the limits of integration right here. We go alpha f4 and plug in y1. We know that it was in terms of x. Well, do we know that that's pi over 12? Well, we can go ahead and check. We know that pi over 12, it's probably going to be close. Oh my gosh, will you look at that? It's exactly the same thing. So we wind up getting, in terms of our integration, exactly what we get when we plug it into the calculator and let it do its magic. Okay? Well, I'm going to try to get to as many different varieties of functions because I don't want to leave you in a lurch and have you blindsided by something on a test or a quiz that you haven't seen. So let's go ahead and look at, let's go -1 to 1 of e to the x dx. Well, remember, you're going the opposite way from differentiation. So remember that the derivative of e to the x is simply e to the x. Okay, so if they're identical, then going backwards ought to be really easy. E to the x from -1 to 1 winds up being e to the 1 minus e to the -1, or e minus 1 over e. It really is that easy. Okay, and we can get a decimal approximation for that, or we can get it in terms of a common denominator or whatever. Okay. Well, 1 over e is about 1/3, and e is about 2.7, so it probably winds up being somewhere around 2.3 something or other. Okay. But that is, of course, the exact value right there. Now notice that we didn't do anything silly like negative 1 to 1 of e to the x squared minus x dx. Okay? We have not done anything like that yet. Okay? Or, you know, actually that would be a little bit more of a hassle, and you'll understand when we actually get there. E to the 2x minus 2 or something like that. Because remember, this right here is not just a simple function. That is a composite function. And a whole different, well, not a whole different method, but a much more robust method must be employed in order to undo the chain rule. Okay? What we're going to be doing right here in this particular section has nothing to do with undoing the chain rule. We're just going to try and undo very simple and straightforward functions as we move forward. Alrighty, let's go ahead and do something that's polynomial but multiple terms. Let's do 3 to 0 of 2t cubed minus 6t squared dt. Now, should that freak me out? Well, here's the thing. You're going from 3 to 0 instead of 0 to 3. That's not the order that we're used to seeing things in. Okay? But can I basically turn that into 0 to 3, plop a negative out in front, and call that 2t cubed minus 6t squared dt? I certainly can. Okay? And that might actually be the right way to do it. Now, will you still get the right answer if you go ahead and integrate here and actually, do the, f of 0 minus f of 3? Absolutely. So you could change it if that kind of wigs you out, the fact that it's 3 to 0. Or you can just keep it as it is. Okay? Let's go ahead and just keep it as it is. Let's go ahead, and we know that it's going to be, we're going to bring along the 2 for the ride, and the t to the third, when you integrate it, is going to be t to the fourth over 4. So you wind up getting 1/2 t to the fourth. This right here, this becomes t cubed over 3. Well, that 3 in the denominator cancels out with the 3 inside the 6. So you wind up getting 2t cubed, like that. Well, here's the thing. We know that when it's a polynomial, if one of the limits of integration is 0, I don't really have to do anything about that because it's 1/2 0 to the fourth, right? Minus 2 0 cubed. Well, I could have seen that one coming, right? When you plug in 0 for the variable, it's just 0. 1/2 3 to the fourth minus 2 3 to the third. Well, now the fact that I have a difference right here with a negative out in front, I know that I could have flipped that difference right there. Could I have, instead of putting the negative out in front, could I have gone 0 to 3 of 6t squared minus 2t cubed dt? Absolutely. And you'll notice that I actually started to put a 6 right there, and some of you probably caught that and were wondering that all along. That is a perfectly legitimate way to do it as well. That is obviously going to be 0, okay? And so I know that 3 to the fourth is 9 squared, so that winds up being 81/2. That is 27 times 2, so that's 54. And so I wind up getting 54 minus 81/2, which is 40.5. So that actually winds up being 13.5 as the area under that curve. Okay? Let's do one more and then we'll call it quits for this particular video. Let's do a trig one. That's always fun. How about 0 to pi over 6 of secant theta tangent theta d theta? Well, I happen to know that that integrand right there is the derivative of secant, right? So if the derivative of secant x is secant x tangent x, then I know if I'm going the other way, this actually winds up being secant theta from 0 to pi over 6. Well, secant of pi over 6 minus secant of 0. Well, what's secant of pi over 6? Well, I know that cosine of pi over 6 is what? Well, cosine of pi over 6 winds up being root 3 over 2. Okay, so this is 1 over root 3 over 2. And then secant of 0 is 1. So that's 2 over root 3 minus 1. And then, of course, you can give a decimal approximation, or you can change the form of that and actually put it in terms of a single expression or whatever. What form the answer comes in has everything to do with, well, first of all, your teacher's preference, but second of all, what you're going to do with it. So that might actually be just fine, depending on your teacher's proclivities. That sort of brings us to the end of this particular video. Let's do one more on the first fundamental theorem of calculus, and then we'll get going on the second fundamental theorem of calculus. There may be a total of about 5 or 6 videos on this, but I want to make sure that you are well prepared. If you think you got it, skip over the next one and hop right to the second fundamental theorem of calculus. And if you have any questions, as always, you are more than welcome to email me. Bye.